Okay, in this segment we are going to look at just one more property of tensors, and then go on to topics that will bring us much closer to continuum mechanics itself, rather than just this just these definitions and properties of vectors and tensors. Okay, so the property that I'm going to talk about is just the eigenvalue decomposition. Right? It's a familiar one, but we're going to use a specific twist on it for certain types of tensors. Okay, so we're going to start by recalling the eigenvalue problem. Okay. Okay, and the way this works, we're going to use our notation from linear algebra, but we're really going to talk about this for tensors, okay, not just for matrices. Okay, so as before, we have A belongs to GL3. Okay, and let's suppose that U is a vector. Okay, furthermore, let's write lambda is a scalar. Okay, that's what we have. Now, as you recall, the standard eigenvalue problem from linear algebra is the following, right? So the standard eigenvalue problem right? Standard eigenvalue problem is A of u equals lambda times u. Okay? And the way we pose this is the following. Given A, find u and lambda such that A of u equals lambda u. Okay? So, given A, find u and lambda such that this holds. Okay? Now, and you know that once this holds, we know that u is called an eigenvector, right? And lambda is the corresponding eigenvalue. Okay? Now, we're not going to get into details here about how we actually solve this eigenvalue problem and so forth. We're just going to sketch it out. Okay? We're not going to get into detailed solution techniques. Right? You recall that the way this proceeds is the following. Okay? What this implies, you will recall, is that A minus lambda multiplying this tensor, right, which can be written as the identity matrix, all of this acting on u has to be equal to 0. Okay? All right. Now, you recall that to find non-trivial solutions of this problem, okay, so in order to find non-trivial solutions, okay, what one must have is that the determinant of A minus lambda times 1 with tensor 1 equals 0, right? That's the condition we apply. What that condition gives us is the so-called characteristic polynomial. Okay, so this leads to the characteristic polynomial okay, in lambda. Okay, so the characteristic polynomial in lambda. Okay, and that takes the form lambda cubed minus what I will write as 1. It's a scalar, and I'm going to say what this is, right? So you get lambda cubed minus 1 lambda square plus 2 lambda minus 3. So this is the characteristic polynomial. And of course, we need an equation, right? Because what we had on the previous line, determinant of a minus lambda 1 equals 0 is an equation. So we have this equals 0. Okay? So this polynomial on the left-hand side in lambda is the characteristic polynomial. Now, 1, 2, and 3, of course, these are Roman 1, 2s, and 3s, 1, 2, and 3, are the so-called principal invariants of A. In particular, 1 equals trace of A, 2 equals 1/2 of the trace of A squared, right, the square of the trace of A, minus the trace of the tensor A square. And 3, Roman 3, is simply determinant of A. Okay? So these are the so-called principal invariants of A. They define the characteristic polynomial, and the solution of the characteristic polynomial gives us our eigenvalues. Okay? The characteristic polynomial has the same power as the spatial dimension of the corresponding tensor, right? The physical spatial dimension in which the tensor acts, right? So we're working in three-dimensional space, and therefore we see that the order of our polynomial is 3, right? It's a cubic polynomial. All right, so I'm sure you're all familiar with this. There's an interesting property of tensors, which is something called the Cayley-Hamilton theorem. Right? And this basically tells us that you can take that characteristic polynomial, and instead of writing it in terms of lambda, you can actually write it in terms of the tensor A itself. Okay? So in that form, it would appear as A cubed minus the first principal invariant times A square plus the second principal invariant times A minus the third principal invariant times our identity matrix, or our tensor 1, all of this equal to the 0 tensor. Okay? And this thing essentially tells us that a tensor A essentially satisfies its own characteristic equation. This is a result that we may use at some point to prove certain conditions and to develop further results in continuum mechanics. Okay? To round off this segment, I'm going to give you a special kind of way to write out a tensor, provided that tensor is symmetric. Okay, and this particular way of writing this symmetric tensor derives from the eigenvalue problem. Okay, we are going to look at the spectral decomposition of symmetric tensors. Okay, so as always, A belongs to GL3, and furthermore, A equals A transpose. Okay, now if we have this sort of situation, then let's suppose that because we're working in 3 dimensions, A has an we can do the eigenvalue decomposition of A, we can get the 3 eigenvalues and eigenvectors. Okay, so let's suppose then that lambda 1, lambda 2, lambda 3 are the eigenvalues of A. Okay, and let me suppose furthermore that U1, U2, U3 are the corresponding eigenvectors. Okay. Now, because A is symmetric, there are certain nice properties that follow for the eigenvalues as well as the eigenvectors. Can you recall what they are? What can you say about the eigenvalues of a symmetric tensor or alternately a symmetric matrix? Think about it for an instant. Okay? All right. Since A equals A transpose, that is A is symmetric, right? So that's symmetric. Okay? What it implies is that lambda 1, lambda 2, lambda 3 are indeed reals. Right? Right? They're real numbers. Okay, they're not complex numbers. Right? Okay. Furthermore, what it says is that U1, U2, U3 can be defined so that they form an orthonormal set. Okay? Okay? With all of this in place, we can write out the spectral decomposition of A. All right? It is the following. A equals the sum capital I going from 1 to 3 of lambda sub I ui tensor ui. Okay. So this holds in this holds in general. Now this form is most convenient if the eigenvalues are distinct. All right. So this holds if lambda 1 is not equal to lambda 2 is not equal to lambda 3. Okay. If we have two repeated eigenvalues, right? So if we see that lambda 1 is not equal to lambda 2 and lambda 3, but lambda 2 and lambda 3 are equal. Okay? In this situation, we can write A as the following. We can write A as lambda 1 u1 tensor u2 plus lambda 2 or lambda 3 because they are the same times our tensor 1 minus u1 tensor u1. Okay? All right, this is if two of the eigenvalues are repeated. In the case that all three eigenvalues are repeated, right, if we have lambda 1 equals lambda 2 equals lambda 3, okay, in this situation we have A equals lambda 1 times our tensor 1. Okay? Right? Now, if you think about it, this very last result tells us that our tensor 1, okay, can be written in general. Okay? What this implies is that this tensor is always writable, so to speak, as the following sum. Okay, if u1, u2, u3 are an orthonormal set. Okay, in particular, this tensor 1 is in fact E1 tensor E1, well, it is just EI tensor EI, where the I index is repeated and therefore a sum is implied on it. Okay, this is again a very useful property that we will use many times. As a final statement, I should just say one thing. I've been calling this tensor 1, I've been sometimes referring to it as the identity matrix. It is properly called the second order isotropic tensor. Okay, so 1 is properly called the second order isotropic tensor. Second order because it's a tensor of second order. It has two indices, as we saw when we wrote it in terms of the Kronecker delta. It's isotropic because as we move along, we will see that the fact that it is an identity matrix essentially tells us that it takes any vector and gives you back the same vector, right? In the context of what it does for space is that it sees all of space as being the same. It doesn't care about directions in space, okay? We'll see a little more about this. Essentially what this says is that if you take a vector here and you apply the isotropic tensor to it, it just leaves it the same. And it does the same for any vector. Okay, so in a sense, it doesn't care what the orientation of this vector is. It doesn't care whether it's oriented this way or that way. It just sees it as itself, right? So this is, in some sense, this tensor does not recognize direction. It sees all directions as the same, and therefore it's called isotropic, which, as you may know, means sort of impervious to directions. Okay? All right, we'll stop there for this segment.